In this lesson, we will prove several properties of homomorphisms. So first, let's recall the definition of a homomorphism. Recall that a homomorphism phi from a group G to a group H is a mapping that preserves the group operation. So that is phi of x times y equals phi of x times phi of y for any elements x and y in G. We say phi is an isomorphism if phi is both one-to-one and onto. Some other definitions that we want to recall: the image of phi is the set written phi of G. This is the set of all images phi of little g such that G is in the group G. The kernel of phi is the set of all elements of G that get mapped to the identity. So we write this as kernel phi. Again, this is the set of all elements in G that get mapped to the identity. I'm going to distinguish the identity element of H as 1 sub H as opposed to the identity element of G, which is, I'll write as 1 sub G. Now, we actually stated earlier that the kernel of phi is actually a subgroup of G. So we will soon show that the kernel of phi is actually a normal subgroup of G, and later we'll see that every normal subgroup can be written as the kernel of some homomorphism. Now we begin proving some properties of homomorphisms. So I want to let phi be a homomorphism from groups G to H. And I'm going to let little g be an element of group G. First property, phi of the identity is the identity in H. So this property tells us that the identity of one group gets mapped to the identity of the other. Second property, phi of G to the power n equals phi of G raised to the power n for all integers n. And so in particular, phi of G inverse equals the inverse of phi of G. Thirdly, we'll actually show that the kernel of phi is actually a normal subgroup of G. Fourth, phi of A equals phi of B if and only if A kernel of phi equals B kernel of phi. So these are cosets. Phi of A equals phi of B if and only if the left coset A kernel phi equals the left coset B times kernel of phi. 5. If the order of element G is finite, then the order of the image phi of G actually divides the order of G. And our last property, if phi of G equals H, then the pre-image of H which is the set written as phi inverse of H. So this is the set of all elements X and G that get mapped to H. So set of all X and G such that phi of X equals H. This set equals the left coset G times kernel of phi. So if phi of G equals H, then the set of all elements that get mapped to H equals the left coset G kernel of phi. So now let's begin our proof with part 1. So for part 1, notice that the identity element of H times phi of the identity element of G just equals phi of the identity element of G, since phi of the identity element of G is an element of H. But then I can write the identity element of G as 1 times 1, and then by the definition of a homomorphism, we have this equals to phi of 1G times phi of 1G. So if you look at the first expression in this chain on the left and the last expression on the right, we can cancel phi of 1G on the right to obtain that the identity element of H equals phi of the identity element of G. Now let's begin the proof of property 2. First, let's assume that n is a positive integer. So for n positive, phi of G to the power n is equal to phi of G times itself, a total of n times. And then we can just apply phi to each factor. So this is phi of G times phi of G all the way out to times phi of G. And we have n of these factors of phi of G, so this is the same as phi of G to the power n. So the property holds when n is positive. Well, property 1 is just the case when n equals 0. So now let's assume that n is negative. Well, then negative n is positive. And we know that the identity element of H equals phi of the identity element of G. But then I can rewrite this as phi of g to the n times g to the minus n. By using the property of homomorphism, this equals phi of g to the n times phi of g to the minus n. And since minus n is positive, I can rewrite the second factor as phi of g to the minus n power. So now we have the identity element of h equals phi of g to the n times phi of g, the quantity, to the minus n. So now if I multiply both sides of this equation on the right by phi of g to the n, so by multiplying on the right by phi of g, the quantity, to the power n, we have phi of g to the n equals phi of g to the n. So we've shown that this formula holds for any integer n. And so a particular case, when n is -1, we see that phi of g inverse is equal to the inverse of phi of g. Now for the proof of part 3. First we show that the kernel is actually a subgroup, then we'll show that the kernel is a normal subgroup. So first we show that the kernel of phi is a subgroup of G. Well, by property 1, the kernel phi is not empty because the identity element of G maps to the identity element of H. So see, the kernel phi is non-empty. So now let x and y be in the kernel of phi, and we'll show that x, y inverse is in the kernel of phi, and therefore the kernel is a subgroup. So to show that x, y inverse is in the kernel of phi, we're going to take phi of x, y inverse and show that this has to equal the identity of H. So what this equals, phi of x times phi of y inverse. Then by property 2, this equals phi of x times phi of y, and then take the inverse. But phi of x equals the identity element of H, and phi of y equals the identity element of H. So this equals the identity times the inverse of the identity, which is just the identity. So this whole product just equals the identity of H. So we've just shown that xy inverse is in the kernel of phi, and therefore the kernel of phi is a subgroup of G. So now, to show that the kernel phi is normal, let's let x be in the coset A kernel of phi A inverse for some arbitrary element A in G. Then I can write x as A y A inverse for some y in the kernel of phi. And then if we apply phi to x, phi of x is equal to phi of A y A inverse, which again, breaking this up, equals phi of A times phi of y times phi of A inverse. But phi of y is the identity in H, so this equals phi of A times the identity in H times phi of a inverse, and then by simplifying, this just equals phi of a times phi of a inverse, which is the identity of H. So what I've just shown is that X is in the kernel of phi. Thus, the coset A kernel of phi A inverse is contained in the kernel of phi. And therefore, the kernel of phi is normal. In G. So the kernel of phi is not only a subgroup, the kernel phi is actually a normal subgroup of G. Now we prove property 4 that says phi of A equals phi of B if and only if the coset A kernel phi equals B kernel phi. So let's begin the forward implication. That is, we want to assume phi of A equals phi of B, and we want to show that A kernel phi equals B kernel phi. Well, then the identity of H can be written as phi of A inverse times phi of A, but since phi of A is phi of B, I can also write this as phi of B inverse times phi of A, and this equals phi of B inverse times phi of A. I can write this as phi of B inverse A. So thus B inverse A is in the kernel of phi because phi of B inverse A is the identity element of H. But we actually proved in our lesson about cosets that B inverse A is an element of kernel of phi if and only if the left coset B kernel phi equals A kernel phi. And that's what we need to show. So therefore, if phi of A equals phi of B, then B kernel phi equals A kernel phi. Now for the converse, we can just reverse the previous argument. That is, assume that B kernel phi equals A kernel phi, and then we can deduce by working backwards that phi of A equals phi of B. Next, we prove property 5, that if the order of G is finite, then the order of phi of G actually divides the order of G. So let's assume that the order of G is finite, and let's say that G to the power n equals the identity. So G has order n. Then phi of G to the power n equals phi of G to the n by property 2, and this just equals phi of the identity in G, which by property 1 equals the identity of H. So we've already shown earlier that if an element to the power n equals the identity, then the order of that element divides n. So therefore, the order of phi of G divides n. Now we prove the last part, number 6. So recall property 6 says that if phi of G is H, then the preimage of H equals the coset G times the kernel phi. So what we're going to show first is that the preimage of H is a subset of G kernel phi. Then we'll show the reverse containment. So let X be in the preimage of H. Then that means that phi of X equals H, and we're assuming that phi of G was also equal to H. So we see that phi of X equals phi of G, and then by property 4, we can conclude that X kernel phi equals G kernel phi. Now, every element is in its own left coset, so X is an element of X kernel phi, and therefore X is an element of G kernel phi, because these two left cosets are the same. So we've just shown that the preimage of H is a subset of G kernel phi. Now we'll show that G kernel phi is a subset of the preimage of H. So let's let X be in the coset G kernel phi. Then I can write X as G times Y for some element Y in the kernel phi. And then I need to show that phi of X equals H. So let's take phi of X, then this is equal to phi of Gy. I can write this as phi of G times phi of Y. But phi of G we assumed equals H, and since Y is in the kernel of phi, phi of Y is the identity of H, and so this just equals H. Thus, X is in the preimage of H, because phi of X equals H. And this finishes our proof of the 6 properties that we listed about homomorphisms. Next, we present some examples that illustrate the properties that we just proved. So first, let's look at this problem where we determine all the homomorphisms from the integers mod 12 to the set of integers mod 30. First, we'll note that any such homomorphism will be completely determined by the image of 1 under this homomorphism. So first, note that if phi is such a homomorphism, and let's assume that phi of 1 gets mapped to the integer n in the integers mod 30, then phi maps the integer x. Well, I can rewrite phi of x as phi of 1 plus 1 plus 1, a total of x times. And this equals phi of 1 plus phi of 1 all the way to plus phi of 1. And this is a total of x terms of phi of 1. So this just equals n plus n all the way to plus n. And we have a total of x of these n, so this just equals n times x. So this is why, if we know where the integer 1 is being mapped to, we can completely determine the definition of this homomorphism. So phi is completely determined by the image of 1. Well, let's look at property 5. We know that by property 5, we know that if phi of 1 equals n, then the order of n divides 12. And by Lagrange's theorem, or corollary to Lagrange's theorem, since n is an element of the integers mod 30, the order of n also divides 30. So we know that the order of n divides 12 and the order of n divides 30. So the order of n must be an element of the set 1, 2, 3, or 6. These are all the common divisors of 12 and 30. Well, if the order of n is 1, then n equals 0, and we have the trivial map, that is, every element of Z mod 12 gets mapped to the identity element 0. If the order of n was 2, then n must be 15. This is the only element of the integers mod 30 with order 2. If the order of n is 3, then n could equal 10 or the inverse of 10, which is 20. And if the order of n is 6, then the elements of Z mod 30 that have order 6 are n equals 5 and the inverse of 5, which is 25. So what we see that any homomorphism from the integers mod 12 to the integers mod 30 is defined by phi of x equals nx, and the possibilities for n are 0, 5, 10, 15, 20, and 25. So as a subgroup of the integers mod 30, this is actually the subgroup generated by the integer 5. So we see these are the only 6 possibilities for a homomorphism from the integers mod 12 to the integers mod 30. Now for another example, let phi be a homomorphism from the integers mod 30 to itself, and let's suppose that the kernel of phi is the set 0, 10, and 20. Further, let's suppose that phi of 23 is 9. So 23 gets mapped to 9. Then let's find the pre-image of 9, that is the set of all elements that get mapped to 9. Well, by property 6, we know that the pre-image of 9 must equal 23 plus the kernel of phi, since this group is written additively. So this gives us the set 23 plus 0, 23 plus 10, and 23 plus 20. But then when we reduce mod 30, it gives us the set of integers 23, 3, and 13. So these are the three elements that get mapped to the integer 9 by this homomorphism. Next, we'll prove some properties about images of subgroups under homomorphisms. Let phi be a homomorphism from group G to group H. And let K be a subgroup of G. Then the image of K, phi of K, would be the set of all elements phi of little k, such that little k is an element of the subgroup K. And property 1 tells us that if K is a subgroup of G, then phi of K is a subgroup of H. So the image of a subgroup is a subgroup. Second, if K is a normal subgroup of G, then the image of K is a normal subgroup of the image of G. So property 2 tells us that homomorphisms preserve normality. Property 3, if K is cyclic, then the image of K is cyclic. Property 4 tells us if subgroup K is abelian, then its image is abelian. Property 5, if the order of the kernel is n, then phi is an n to 1 mapping from G onto the image of G, phi of G. So these statements show that many properties of subgroups are preserved under a homomorphism. Let's begin the proof of property 1. Let's begin the proofs. So for statement 1, since we're assuming that K is a subgroup of G, the identity of G is in K. And thus the identity element of H, which is phi of the identity element of G, is in the image of K. So we see that the image of K is non-empty. Now let X and Y be in the image of subgroup K. So to show that the image of K is a subgroup, we're going to show that XY inverse is also in the image of K. Then X equals phi of M, and Y equals phi of N for some elements m and n in subgroup K. Well, since m and n are in subgroup K, then m and inverse is in K. Again, this follows since K is a subgroup of G. Then xy inverse is phi of m times the inverse of phi of n. But then I can go combine this to be equal to phi of m n inverse. And since mn inverse is in K, this is an element of the image of K. So we can conclude that the image of K is a subgroup of H. So for the proof of statement 2, let's suppose that K is actually a normal subgroup of G. So we will show that A phi of K, A inverse, is contained in the image of K for all elements of the image of G. So let X be in A times the image of K times A inverse for some A in the image of G. Then X can be written as A phi of some little k times A inverse for some little k in subgroup K. Now since A is in the image of G, A has to equal phi of little g for some element G in G. Then X, which is A phi of little k A inverse, can be written as phi of G, phi of little k, phi of G inverse. But I can combine this to equal phi of GK G inverse. But now since K is a normal subgroup of G, we see that little g, little k, little g inverse is an element of K. So the phi of this element is an element of the image of K. Again, this follows since G little k G inverse is an element of K because K is a normal subgroup of G. So we've shown that an arbitrary element of A phi of K A inverse is in phi of K. Thus, A times the image of K times A inverse is contained in the image of K, and that shows that the image of K is a normal subgroup of the image of G. Next, we prove statement 3. So let K be a cyclic subgroup of G. And we're going to show that the image of K is cyclic. Well, then I can write K as the cyclic subgroup generated by A for some element A and K. By statement 1, we know that the image of K is a subgroup so let X be in the image of K. So then X equals phi of little k for some little k in group K. But then little k can be written as a to the integer n, since K is the cyclic subgroup generated by A. So then X equals phi of a to the n, which is equal to phi of a to the power n. So we see that any element of the image of K can be written as an integer power of phi of a. Therefore, the image of K is actually generated by the image of A. So this is a cyclic subgroup generated by the image of A. We see that the image of K is cyclic. So property 3 says that if K is a cyclic subgroup, then its image is cyclic. Statement 4 says the same thing, but with abelian subgroups. So suppose K is an abelian subgroup, and let X and Y be any elements of the image of K. So then I can write X as phi of M, and I can write Y as phi of N for some elements M and N. In K. Then to show that the image of K is abelian, we're going to show that xy is the same as yx. So xy equals phi of M, phi of N. I can combine this to equal phi of Mn. But now I'm going to use the fact that K is abelian, so I can write Mn as n times M. And then this equals phi of n times phi of M, which equals y times x. So we see that the image of K is abelian. Now for the proof of statement 5, let's recall what the statement says. It says that if there's n elements in the kernel of phi, then phi is an n-to-1 mapping from G onto the image of G. So what this means that, if n elements get mapped to the identity element of H, then every element of H that gets hit by the homomorphism phi gets hit a total of n times, exactly n times. This is what we mean by an n-to-1 mapping. N elements of G are getting sent to one element of H. N elements of G are getting mapped to one element in the image of G. So let's begin the proof of statement 5 by assuming that the kernel of phi has n elements. So we proved that for all H and H, the pre-image of H equals G times the kernel of phi, where G is an element such that phi of G equals H. So So then the order of the preimage of H equals the order of G kernel phi, but this just equals the same as the order of the kernel phi, which is n, and this is true since all cosets of a subgroup have the same cardinality. So G kernel phi has the same size as kernel phi, which is n. So thus, if H is in the image of G, H has n preimages in G. i.e. phi is an n-to-1 mapping. Now for a quick corollary to property 5, we see that if n is 1, that is, there's only the identity element in the kernel of phi, then phi will be a 1-to-1 mapping. And if we know that phi is a 1-to-1 mapping, we already know that phi of the identity gets mapped to the identity. So we have the following corollary. Of statement 5, we see that phi is 1-to-1 if and only if the identity is the only element in the kernel of phi.